Thanks very much, Jack and Trish. Thanks for the invitation to speak. And thanks all of you for coming for what used to be the start of Supercomputing Week, but increasingly feels more like the middle as events work their way back into what is now becoming Supercomputing Month, it feels like. So my talk's titled here, Computing for the Endless Frontier, which was actually the name of the proposal. And as Jack mentioned, the machine is called Frontera. And that's because where Jack is at Oak Ridge, they had already gotten the fact that their next machine is going to be called Frontier into the federal budget between the time we submitted our proposal and the time it was awarded. So we did a little translation. And so now we will be Frontera, but that was the name of the proposal. So, riffing on the fact that the NSF was actually founded after Vannevar Bush wrote a paper in the 40s called Science, the Endless Frontier, that it's the frontier that keeps going. And so a good metaphor for Texas where we are today and moving forward. So because I won a big NSF grant, you have to indulge me for a few minutes because they're going to invite me to speak no matter how bad I am because I've just won this new grant. So let me take through a bit of history. This actually isn't a machine at TACC, but this was my very first Beowulf cluster. I think it was the second one in 1993, so 25 years ago. When I was at Clemson, working with NASA Goddard, Thomas Sterling, Don Becker, et cetera. And at this point for us, clustering was sort of a garage activity, meaning I literally was in Walt Wiggins' garage laminating shelves for this machine 25 years ago. We started TACC in 2001, and we've sort of slowly made our way from a center with like 6 full-time and 6 half-time people and a $600K budget. And we've sort of grown up in sort of professionalism and scale of systems, but systems aren't the only thing that have grown during this time period. And you see we get bigger and bigger as the years go on. And for the first few years, it was, let's write a proposal to win a bigger system. And so all the milestones are bigger system, slowly climbing our way up the top 500 list. 2007, the one in bold there, was Ranger. It's the picture on the bottom. Was the largest open science machine at the time, really the sort of entree for us into being a leader in this field about now 11 years ago. But after that stage, we still kept doing bigger and bigger systems, but the kinds of funding we got, and I think this sort of represents what we've done with Frontera, began to change, right? First it was build bigger systems, then it was systems and viz, and then we started getting into software for bioinformatics. The staff kept growing as we went through there, and we have bigger and bolder systems. Stampede 2 is the one in the bottom corner there, just a couple hours down the road in Austin. You can tell it's from Texas, Lone Star 5 too. But more and more of these awards became about software and domain-specific science, design safe for cyber infrastructure and things like that build upon advanced computing. And I think that's one of the trends we've seen. Convergence of data and AI is something that we should just come up with an acronym for because we're going to hear it so many times this week and we need a quicker way to say it. But along with that has been, as we've had more kinds of users on the systems that we have, those of us at supercomputing centers are asked to do more and more in terms of the amount of scientific workflow. If you look back to those early systems, if we could get them to stay up, and we could hand somebody an account and say, here's your SSH keys and get on and run, that was sort of all we had to do for them, and good science was going to happen. And whereas we still have users who are like that, there are more and more who ask more and more of us. And I think some of what you see in our new systems reflects that evolution as well. So a lot of this we have done with Intel, and I think they've deleted everything I had in my slides. Forwards, there we go. That mentioned, oh, they left the word AMD in there. I'm impressed. So almost all of my other references to other vendors have been deleted, but from the slide deck since I submitted it. But it's important to mention, not only is Intel a partner with us, but we haven't been an exclusive Intel shop, right? We did Ranger with AMD, for instance. We did a system that was called Longhorn. We've done 3 systems called Longhorn. We're in Texas, but with IBM and the power processors. But so, the point being that we evaluate technologies and we pick the ones that are best. Yet Intel has been the one that we've picked the most over the years, including our last 3 large systems have all relied on a combination of different Intel technologies. And I think, first of all, as I said, right now we have virtually everyone's processors in our data center. And so part of it is having the right products. And part of it is having a really good partnership with Intel through the years, where even when things aren't going great, we can have frank discussions about what's not there and find ways to fix it and make the current product better, the future products better. We really feel like we've been able to have productive and responsive input into what Intel does through the various generations of chips, and that's made them a great partner for us, and that's how they've ended up in so many of our systems over the last few years. And so before I talk about Frontera, let me just say Stampede 2 is our current sort of flagship system. It's around 18 petaflops. I guess tomorrow Jack will tell us where that falls on the list this time. But it's a combination of the current generation of Xeon Skylake processors and the Xeon Phis that were codenamed Knight's Landing processors, and they're still both constantly used. In fact, for this quarter, we've got 10 times as many requests as we could satisfy for the machine. They both have long waits. 2 million jobs in the past year for Stampede 2, 10,000 plus people. But across Stampede 2 and Stampede 1, which was also Xeon and Xeon Phi, and Ranger, which was x86 based, but with AMD, we've built a database and kept statistics on all of the last 10 million jobs that have run across our systems. So we have a pretty good idea of what sort of ends up in the slides as the things that are the big science challenges that people run, and then what actually runs on the system and how well they use it. We keep performance counters, memory stats, file system stats, et cetera. And we've used a lot of this to guide our design for Frontera and really all of our future systems. So we've tried very hard to do analytics based on what's running. And we talk about using HPC to solve big data problems. As it turns out, designing HPC systems is also a big data problem. So some of that is factored into it too. So let me say a few words about the system and then I'll come back to that. So Frontera, the thing that I'm here to talk about, is really a 3-part project, which in NSF parlance means I have 3 times as many reviews and documents to do to actually get the thing awarded. But it is to deploy a system next year, and that's the part that we've announced at this point. So probably by ISC, we should be up and running to sort of be the NSF flagship for the largest computations for the 2019 to 2024 or so time frame, so sort of the first half of the 2020s. Then we have to support and operate this, and we'll talk about some of the operations. As again, as the reach of science grows, that's where a lot of the interesting stuff is now. And then we'll plan a potential phase 2 system to replace Frontera in 24 or 25, somewhere in there, with 10x the scientific capabilities for the problems of the latter half of the 2020s. So actually identifying those problems is a bit of a challenge. So, and I'm noticing there's not a clock. We have a very large team. It's never just us. It's certainly not just me that supports one of these machines. My job is to put together PowerPoints and deliver them. But we have a group which I'm apparently very bad at. But we have TACC on the operations side, partnered very closely with Ohio State, DK Panda, on the high performance network software side, and VAPIC, et cetera, with Cornell for online training, and with Texas A&M to help some things we're doing in the onboarding of other campuses, working with our partners across the state. And then in terms of that phase 2 planning, where we really need to understand the science drivers for the latter half, we have a much larger team that involves Caltech and the University of Chicago, Rick Stevens, who's actually heading that, Omar Gattas, Cornell, UC Davis, Georgia Tech, Princeton, and Stanford are all part of our science team. And then again, a large set of partners, but Dell and Intel are building the vast majority of the system. So if you're missing getting the notes down on these slides, come to the Dell thing tomorrow and you'll see some very similar ones. Hardware-wise, what it comes down to in terms of the system is our primary computing system is with Dell and Intel. We're using the next generation of Xeon processors, the ones to follow Skylake. Will be between, closer to 40, but between 35 and 40 petaflops peak performance, depending on where the final SKUs settle out. We'll be interconnected with Mellanox HDR at 200 gig. We'll have Data Direct is providing the storage, and I'll talk a little bit more about the storage, but to rough order, 50 petabytes or so of available storage, and across the various file systems and things we're doing, about 1.5 terabytes a second of I/O. We'll have some single precision compute with those other guys in green, and We'll also have a number of services and servers in front of the machine for moving data, for supporting automated workflows, for APIs, and all of the various services that we need to really run the system nowadays. So with that, let me dive in a little bit around. That's sort of the high-level thumbnail sketch. I'll have a figure and a slide or two. But let me dig down into the why on some of those things. So first of all, on the processor side, why we picked the ones that we did. So again, we've been through a variety of processors and a variety of different SKUs of processors through lots of different systems in the last few years. And again, we've done tons of measurements in what we do. So the first thing we heard, even from reviewers and from lots of people, is what we decided to do was Xeons. Just Xeons, not Xeon and something else, Xeons. And as we did the first round of media interviews, if you're an HPC journalist and you write about these things, you might find that a little bit boring. We found that the user version of boring is what they call useful, and that they compile their code and it runs on the system. So there's not one user in our user base who has to change their code to take advantage of a higher clock rate. So what we've done is, rather than sort of targeting the SKUs of Xeon that we've normally hit, and if you look over the last few generations, everybody's targeting the sort of 130 to 145 watt parts, and we moved up to the top of the bin, which in the current generation of Xeons would be the sort of 205, 210 watt parts that are out there. And we're going to use those, and they're hot, and they're hard to cool. There's no air-cooled way to run them, so we're going to water cooling. If you measure in terms of peak flops, they're probably not the single most power efficient thing if you just take watts over peak flops. But if you look at how people use them and their ability to realize effective performance out of them, we think for the users, they're the most effective way to get power per watt. So we could use very low power, much lower clock rate chips, but we'd be less efficient on them. So our analysis is that the thing users want, and frankly, most of our science users think of power efficiency as our problem, not their problem. But we still have to meet them in the middle somewhere on this. But if there's higher clock rate, everyone can use it. So versus our previous systems, you're going to see on the Xeon side, higher clock rate, slightly higher core count, higher main memory speed. And any numbers I would have put in here, Intel won't quite let me say yet on the next generation. But nonetheless, pushing up those things is as close to free performance as we can give to our users, and frankly, that's what they want. None of them are interested in, well, none is an exaggeration, but few are interested in being a CS experiment and how to find different coding models unless we can hide it effectively in libraries that they can use. Across the spectrum, looking for all of the different applications that we have to support in the NSF space, and there really is a wide range that really do a lot of things, but if you just sort of average workload versus dollar, as I compete with the dishes out there, we found the more we can crank the clock rate, the better off we are. So these high power SKUs were really the right ones for us. And although there's ways to get better performance or even better performance per dollar on very specific applications, it's really hard to do any better than a fast Xeon across the whole workload. So that drove our processor decision. So we've done a similar thing with file systems, and those of you who run systems or even just use systems know that file systems are often our weak point in what we do, because whereas we've done a really good job of isolating users to their own compute nodes, and it's hard for something that one user does that screws up a node, which in theory the system software protects you against, but in practice it really doesn't. It's hard for one user to affect another in terms of what they do on the compute nodes. But for the file systems, that's totally not true, right? We know from many years of painful experience that there are plenty of ways that users can come up with some pathological case of on the file system. We think that maybe they intentionally write while one fork open or something like that, but it feels that way some of the time. But if they generate enough metadata traffic, we know that one user can impact another. And we've done some software things to mitigate that. Little known secret is that on some TACC systems, we will put sleeps between your open calls to limit you to so many per second. So the file system doesn't fall over. But nonetheless, our analysis of all the jobs that run on the file system is we have users who care about bandwidth. We have users who care about capacity. We have users who care about the number of inodes they consume who are generating millions of files, or IOPS who are doing small transactions. But we've never had a user stress all those things at once. So it really seems counterintuitive at this point to keep building one giant Scratch file system that everyone shares. And I think the real sort of technological decoupling that we got is we used to drive the capacity in our Scratch file systems by getting enough spindles and network ports to get the bandwidth we need. But the age of solid-state storage, NVMe drives, et cetera, have made that not the case, right? We can build a file system tuned for performance that isn't driven by capacity, and then we can build capacity in separate file systems. So we've actually split the file systems into 4 pieces. We'll have 3 Scratch file systems, each in the 15 or so petabyte usable range, that will round robin users to. So at least there's only a 1/3 chance that user running while one fork open will take out the file system that you're on. And for the high IOPS one, we're doing a sort of a 1.2 terabyte, all NVMe, several petabyte file system that you will have to opt into by showing us that you have the I/O demand to use it, and only very select users. It's sort of a scratch for the scratch. But we're not doing it as a burst buffer. We're not going to run it as part of a storage hierarchy. We're not going to try and do any migration. We're just going to manually have users move between the file systems. And everything POSIX. Again, nothing exotic on the system side for this. So that sort of puts us here in terms of what the system looks like. Again, what we used to call the login nodes has become a steadily more diverse set of things as there's more and more services that people want to put in front of the systems. We have REST APIs and other things at this point. But login, data mover, gateway, and API nodes, single and double precision, compute systems, the high-speed interconnect, and then lots of kinds of storage and lots of gateways to get to other kinds of storage as well. More on that in just a moment. So, Lisa, how am I doing on time? So just a brief word on infrastructure. I mentioned these chips run pretty hot. So we're going to have to do a lot of cooling. We're going to use a lot of them. By the way, I skipped this, got deleted. But we'll be ordered to get the performance we need. We'll be somewhere over 8,000 compute nodes. Again, exact number remains non-disclosure, but north of 8K is a good bet. So that's going to push our peak power into the realm of 6 megawatts. We're also pushing 65 kilowatts per rack. So we'll be doing direct water cooling of the racks and the chips at this point. We're using the CoolIT solution that Dell has integrated with their racks. For the main compute racks, for those other chips, we're going to immerse them in oil with GRC and have an oil-immersed cooling system. So there's a lot of infrastructure associated with this. It does fit in our current data center. I'm getting asked about that a lot. Surely you're building an expansion. No, we're putting racks in like 2 months. So we're just fitting them very densely into the space that we have. But we will have some solar inputs, and about 1/3 of our power is coming from wind credits at this point too. So lots of power, but we're greening up the infrastructure where we can. So I'll come back on phase 2 briefly, but I did want to say part of phase 2 is in addition to the main system, since we actually have this longer term commitment from NSF to look at what will come after, we'll be building some prototype systems as well, and we'll be openly allocating them to the users who run on Frontera. So we'll have some with us. We'll have an FPGA-based system. We'll have Optane MVDIMMs in a system. We'll have a quantum simulator stood up at Stanford. We'll have some in the public clouds with all the providers. One of the first ones, again, there'll be the FPGA one with Altera, now also part of Intel. And then we'll have an Intel Optane set of nodes that we'll explore different use cases for as well. So in an effort to stay on time here, we won't delve too deeply into that. I think that'll come up later. So, but part of our goal is to have any system that we build in phase 2, like we did in phase 1, be the result of stuff that we've actually yet users run on, that we've been able to measure their application performance, and that we know they're actually going to adopt. If we stand up a prototype and we allocate it to all our users, none of them use it, it's a pretty good sign we shouldn't build a bigger one. So we'll start small and build out. We'll also be keeping pretty close tabs on what's going on in the rest of the world as we move toward phase 2. So I mentioned that makes operations sort of the more interesting part. Those of you having to listen to this may not agree with that assessment, but so we'll do all the things that we normally do to support systems, and so everything on the list that I'm not going to read here are sort of the traditional activities that you do when you support a big system, and this is just the baseline from which we measure against. So none of that is new and exciting. It's still hard. I have to keep pointing out to funding agencies that just because we've always done this before doesn't mean you don't have to pay for it anymore. Takes a lot of time and energy to do all those tasks. But you've all heard that story before, so let me skip that. The other stuff that everybody sort of should do that isn't really new, but is not in all the stacks will be auto-tuning MPI around the specific architecture, and the topology of the day, even as links fail. To keep track of it, we'll be doing automated performance mining, monitoring and data mining, as we've done through our last 10 million jobs, doing Slack for user support, because we have less than 10,000 users on this one, a smaller community to talk to. But we're going to have some new sort of operational activities as well. And before I mention those, I need to say just a thing or two about the science drivers around it. And I think this will be the theme you see in every talk. Dieter and I were actually saying we could probably switch slides, given the way that our centers operate at this point. That we have many themes in common. We, being humble people, are decided that's just because we're right. And if these are the right answers, everybody should be doing them. But again, we have this changing face of our workload in HPC, data analytics, big data, ML, AI, deep learning, blah, blah, blah. The thing we need an acronym for, we just called that advanced computing, staying out of the HPC world at TACC. Brilliant move by my predecessor to do that. But nonetheless, it is true that the workload does not look like the workload used to. We used to simply measure scale of big computational science by number of MPI tasks in a lot of ways. And that's still certainly a valid measure for many, many types of simulation problems that we see. But we see a lot of other things, people asking for other things. Part of it is the communities they come from. Part of it is the nature of the challenges they faced. Part of it is everybody expects things to run on their phone and be able to press a button and be able to do things, but we see more demand, not just for big data and machine learning, but sort of the modes that go with that, interactive computing, real-time interaction with data, Jupyter notebooks, event-driven data processing, right? Data shows up from a satellite pass or a sequencer, you automatically start a workflow associated with that. They want support for reproducibility, support for data reuse, support for sharing of data, support for collaboration, web front ends, all of these things that used to not be part of the HPC job, but we increasingly believe are a part of the HPC job, because ultimately we're the place that you support computational science that doesn't fit on your desktop. And many of the teams don't have the expertise to deal with these on their own. So, we have simulation for the things where we have complete models. We have machine learning where we have a lot of data but lack complete models or to enhance the models. We have all of these other tasks, and frankly, most of the problems we see now to some degree blend all three, right? So we still have our big computational problems. I talked about LIGO on this stage in whatever city we were in last year. And we still do this kind of thing, which is, and actually we also do the viz, but your traditional very big simulation. This is colliding black holes, or yeah, that's black holes. We did neutron stars too, but the large-scale simulation plus large-scale viz, but the kind of challenge we face now, even in astronomy, our traditional numerical modeling type topic, now it's multi-messenger astronomy, where you're doing data analysis from LIGO and targeting the telescopes at things LIGO observes. We're going to do massive downstream data reduction for SKA and LSST, and then you do data mining on those databases. So they're, again, blends of traditional simulation, data analysis, machine learning. Like I said, I'm sure other people will have many examples of this as well. Same thing in what we do with natural disasters, right? Hurricane modeling is probably one of our oldest numerically driven, or weather modeling. Traditional PDE-based, numerically driven type topic. Yet nonetheless, nowadays we see this blended with real-time data assimilation from sensors. We see this blended with machine learning from past storm databases. And it's the combination of those things that are making the improvements. The numerical methods sort of plus at this point. So our natural disaster support has gone from our traditional seismic and weather simulations to post-disaster image scanning and assessment from drones and UAVs. And again, blending these modes of computation. And then the more social-driven problems, right, where we're using machine learning. There's 8 zettabytes on the deep web now. I think I've read 20 zettabytes expected to be created in digital data next year. And everything from arms trafficking, human trafficking, from social media mining, to digging into databases of public health information to find child maltreatment and neglect. These start becoming geospatial data problems in a lot of ways. We've added capability there. But many things sort of end to end at this point that we have to deal with. So With that said, we've started adding different kinds of support activities around these big systems that you don't normally necessarily associate with big science, but we think leadership science is going to have these just as much as smaller and throughput science. And so part of that is containerization, which we think of as less about cloud and more about good software management at this point, and getting the right ecosystem of packages. So we'll have full containerization support on the machine. We'll have support for controlled information. It's coming, give up. People are fighting, but all data will be protected in one way or another in the next few years. So we're biting the bullet and just supporting that everywhere. Persistent virtual machines to support persistent services. I've mentioned this, whether it's Globus for data transfer, OSG web services for LIGO, REST APIs for gateways. We will have more, we have event-driven services through REST for flow cytometry machines that put in data and you need to update the corpus of data for a machine learning analysis. All of these persistent services are part of the big science workflow now too. So we're building those in, and of course that means eventually we're going to have to actually build some gateways, so rather than simply working with all the gateway communities, we'll have default ones for Frontera from everything from geospatial to machine learning and back again. Probably not all on the first day because there's a lot of code to build there. So system support has evolved just as much as the system has over the last few years. So we'll be leveraging things all around the ecosystem. None of these things, which I like to think of as big research instruments, really stand alone. They live in the context of both other systems, storage, compute, and network fabrics that we have at TACC and around the community. I think there's now there's two OSNs, an open storage network and an Oklahoma storage network. So you can pick your favorite as a place to publish data. And we'll be working with the clouds, which a lot of people find surprising, but I think is essential at this point. So I think through the last, 15 SCs, there's always been the HPC versus the cloud panel, and the last 10 Salishans and 900 meetings in DC. Should we use cloud or should we use HPC? And so I'm going to say for the 500th time, and it's not going to get through now any more than the first 499, it is not an either-or question. There are things that the cloud is good at. There are things that HPC is good at. We can coexist, despite what they're going to tell you at all the booths on the floor. In many ways, we're just a specialized cloud. In many ways, we're the cloud way before the cloud. But we will utilize the strengths of the cloud. You will have the option to publish your data through Microsoft, through Amazon, or Google from Frontera. We will provide DOIs that will go on there. You might want to use a VDI, virtual desktop interface, through one of those. You might want to use an NLP tagging, natural language processing service, or an image tagging service as part of an automated workflow between the cloud and Frontera. And we're actually buying some cloud time to support these kind of services, and also so that we can prototype faster as we think about phase 2, right? We do a lot of systems at TACC. Certainly we're deploying something every year. Those guys are deploying every 2 weeks. Right? So they have every new chip from every vendor, and we're going to make those available too. So again, we understand what's going to work there. So with that, those prototypes and cloud partnerships are one aspect of phase 2, but there's a lot more to do. I'll talk a little bit about this at the Frontera BOF on Tuesday, but input from the science community on what the challenges are for the next sort of the latter half of the 2020s, and input from our partners like Intel on the technology side for what we're going to have to do in the latter half of the decade is going to be highly welcome, and we'll have a BOF on that this year and hopefully every year following. So I think I'm roughly out of time. Am I not? So let me just close by saying, and I stole this, so obviously I stole the quote from Humphrey Davy, but I stole using the quote from David Keyes, so just to be fair. But Humphrey invented electrochemistry and sort of added about half the things on the periodic table. And he actually was a humble guy, and he's like, look, it's not that I'm smarter than everybody who came before me, it's that I have a new tool, in his case electrochemistry, but I'm sure he meant to say this about Frontera, right? Because each new scale of these systems is about providing scientists with a new tool to get to that next frontier. So what we're here to do with the Frontera project is to give our researchers this new tool. So thanks to Humphrey Davy for putting that more eloquently than I can. So thank you to all the people who partner with you and give you money, and everybody on your staff in not alphabetical order, so they can't tell if you missed. And when I was looking up Humphrey Davy quotes, I thought there were some others that were good. So I will just stop there. I'm going to leave this quote on the screen. So thank you very much.
Stay there. Don't move. So I have a question.
Oh, okay.
Yep.
I'm not off the hook yet.
So you're not quite off
Apparently
the
I should have talked a little bit longer.
That's right. Let's see, given that this is the 20th anniversary of Xeon processors, and that TACC has leveraged Intel technology over the years. What's been your experience in the advantages of leveraging Intel architectures?
So experience in the advantages of leveraging Intel architectures. So obviously a huge amount has changed in that time frame, right? 20 years ago we were dealing with single socket and a very different balance of memory bandwidth to compute, and so many other things. But frankly, what's driven us down the path that we've been on for the last 20 years with many cores and with sort of less memory bandwidth per core perhaps, or per flop anyway, is the physics, right? It's not really something that's been driven by a vendor, it's been driven by the way things had to go. So I think for us, being able to work closely with Intel to, within the envelope of what is possible, to make adjustments, right? Hey, we care more about power efficiency, we care less about power efficiency, these kinds of trade-offs has been very important. And the second thing, and that I think has always been one of Intel's great advantages, is by staying on the architectural path that they have, we've been able to leverage the very mature compiler technologies and push that software ecosystem forward, because the best processors in the world without something that can generate code for them are just fancy, high, expensive, very hot boat anchors. So, so the fact that we've been able to move in lockstep with both the system software and sort of a consistent plan for architecture over that time has been, to me, a huge advantage. So.
Well, that's interesting. You shared your scientific solution, Frontera. You shared what Frontera will do in terms of the space of HPC and AI convergence. I'm curious, why do you think HPC, the traditional HPC to AI convergence is happening now?
So I think it's a convergence really of several factors. One is, I think the AI people who have been working in that space have realized they need to scale up in many areas, right? Data has driven them past. They've gone through sort of the same evolution we went through in simulation over the last few decades of hey, I have a lot more data and I need to solve a bigger problem, right? Just as we ramped up grid size and everything else. And so they figured out, well, we need to be multi-node. Perhaps people have looked into how to do things effectively on multi-node. And I think as the mathematics have gotten more sophisticated around it, and I think they will continue to do so, right? In the core, it's going to be linear algebra once again, right? Perhaps very small matrices instead of very big matrices in the core operations. But if linear algebra is the key and you need to scale it up, I think perhaps there is a community that has some expertise in those areas that it's time for those fields to leverage. And so here we are, bring your AI.
Thank you very much, Dan.
Thanks, Jack.